Okay, so we'll start with the first question. What is a semiconductor? We don't know anything about the energy bands, etc. We don't know anything about that. But I can still classify what a semiconductor is, what a conductor is, what an insulator is. It's a very a crude classification, you can say, on the basis of conductivity. Some materials have very good conductivity, which are called conductors. Then some materials will not have any conductivity, very small conductivity, insulator, and semiconductor, as the name suggests, they fall somewhere in between, right? So if you talk about the number per ohm per centimeter conductivity, insulators will have conductivity falling somewhere in this range, right? Below 10 to the power minus 8, very small conductivity. Then you have metals which have conductivity over 10 to the power 4 per ohm per centimeter, like iron or copper. Then you have semiconductors like silicon, germanium. They have the conductivity in this range, from 10 to the power minus 4 to 10 to the power around this, 10 to the power say 1, even more than that, you can say. So if we talk about what kind of elements are semiconductors, so in the periodic table, the group 4 elements, silicon and germanium, they behave as semiconductors. So they have a conductivity which fall in this range. Carbon is not a semiconductor, carbon is an insulator. Some form of carbon, some altered form of carbon can behave like semiconductor, for example, graphene, and not a simple graphene. You will have to do some engineering in that, and in certain conditions it can behave like a semiconductor. But a normal carbon which has a diamond structure, no, it's not a semiconductor, it's an insulator. So these are elemental semiconductors. They are semiconductors by nature. But some of the semiconductors you can create. For example, silicon and germanium, they have both a valency of 4. And we know that the conductivity and conduction properties, they too depend on how many electrons you have in the outermost shell. That's how atoms interact. So conductivity is going to depend on that. So what if I create a compound semiconductor which has an average valency of 4? Silicon, germanium are elements, so they are not compound semiconductor. They are semiconductors by nature, 4 valency. But I can create some semiconductors which are compound semiconductors by mixing element from this group 3 and group 5. So group 3 have the valency of 3, group 5 has the valency of 5, that gives you an average valency of 4, right? So we can create several semiconductors. So compound semiconductor example is, for example, aluminum phosphide, aluminum arsenide, gallium phosphide, gallium arsenide, indium phosphide. Particularly these 3, right? You'll see these in some devices. For example, gallium arsenide is used for RF applications. So it is also a direct band semiconductor, which means it can be used for LED type applications, right, which can emit light. So we will talk about what is direct, indirect band gap semiconductor later on in this course. And then I have indium phosphide, similar property. We'll find this to be used in high voltage devices, high frequency devices. Okay, then there are a few more. For example, indium gallium arsenide. So you mixed 3 elements together, indium, gallium, which are both from group 3, and then arsenide from group 5. Right? So that's also a semiconductor. Okay. So let's talk a little bit about the semiconductor industry. Of course, semiconductors are at the heart of technological progress today, and occupies almost every domain, as I already told you. So you find it everywhere in your computers, smartphones, in the form of chips, AI, automotive, aviation, virtual reality, medical equipments. So they all need these chips which are made of semiconductor devices. Okay, and if you look at the global semiconductor market, so it's a huge market. So in 2021, it was around 590 billion And you can see the breakup of different areas. And then it is expected to grow to over 1 trillion by 2030. So it's a big market, and it's a market where things move very fast. So something which you see today, 10 years later, it's just going to become obsolete. Okay? For example, if we talk about say 10, 15 years from today, we used to have we were mainly using these bulk MOSFETs or planar MOSFETs, right? But then today we talk about nanosheets, FinFETs, right? So these are some advanced semiconductor MOSFETs. So within a span of 10 to 15 years, things move very quickly. Now, if you look at from 2000 to say 2010, there have been so many changes even in the planar bulk technology, right? So Intel came up with, for example, this gate, this metal gate process, and then in around 2012, there was first commercial FinFET, and then FinFET technology. There's several versions of that, and now today we are talking about the nanosheet, and there is a roadmap for next 10 years also, right? So we'll be talking about even more complicated devices, some combination of nanosheets. For example, complementary FET. So there is a N-type device, a P-type device. They are both stacked together, so it's like a 3D device. So that's like a complementary FET to increase the device density, you can say. So all of this moves very fast, and if you do not keep pace with it, so you will be left behind. Okay, so this is a business where things move very fast. Of course, we still use the planar bulk MOSFETs, but I'm talking about for high performance computing, you move very fast usually. So before we move to the actual content, I'm just going to give you some overview of the history of the semiconductors and how we reached where we are today. So it's a long history, starts somewhere in 18th century, 1874, when first metal semiconductor contact properties were observed. So there was a guy called Ferdinand Braun, a young PhD graduate working as an assistant in a university in Germany. So he discovered that if you have a metal and a semiconductor, there is a unilateral conduction. When I apply an electric field across this combination, there is a conduction of the current in one direction, but if I change the polarity, there is no conduction. And normally that doesn't happen in a resistor, right? So that's a unique property he found out. But he just left it at that, did not explain the results, but this was something that was observed first by him. By the way, he's a he later on he became very accomplished scientist. He invented this cathode ray tube, which was used for television, right? So he played a major role in that, and then the phased array antenna in RF. So but he gave the idea of this metal semiconductor contact unilateral conduction. So it's like a diode type behavior. People who are again familiar with the diodes, you might have seen this in your earlier courses, right? So diode conducts only in one direction. It does not conduct in the other direction. So it's like a diode, it's a diode-like behavior. Then, so he did not give the theory, so I'm just jumping to 1942 directly. So the theory came very later. So there was a scientist called Hans Spieth. You might have seen this somewhere. I'll tell you where. So he gave the theory of this metal semiconductor diode, why there is a unilateral conduction. So concept was known in 1874, but it took so many years to understand those behaviors. And there were several groups started working on it, especially, why this semiconductor was being looked upon, because they were actually trying to build wireless communication system. So it was a wartime, and there were a lot of efforts to create these communication systems, right? And they found that these semiconductors can play a major role. They did not understand the theory, but they understand how things operate, right? So, but this guy gave. So he was a physicist, Hans Bethe. He predicted the correct metal semiconductor characteristics, and he gave this theory of thermionic emission of electrons, and that explained the behavior. By the way, this is the same guy. Have you seen Oppenheimer movie? How many of you have watched the Oppenheimer? Okay, so he played a major role. He was a nuclear scientist, by the way. Okay, he was a good solid state physicist, but was also a very good nuclear scientist. So you might have seen this guy in Oppenheimer movie, right? Hans Bethe. So he played a major role in this Manhattan Project and the creation of atomic bomb and all. So going back, 1925, first patent on field effect transistor concept. This MOSFET concept, field effect transistor, it is known since 1925. The concept, not the actual device. So what was the concept? So this scientist, or rather engineer, I would say, Lilienfeld, he gave a concept that you can control the flow of current going through two terminals by applying a vertical electric field through a third terminal. Okay, so these are, say, two terminals here. I can control the flow of electrons which are moving from here to here by the application of an electric field through a third terminal in this direction. Okay, so he gave the concept, did not follow that up, and just left it there. Published this in a United States patent. You can see, what does it say? October 2020, 1925. So very old US patent. You can even find that on Google. So the concept was known very long time back, but it wasn't until many years after this when the first working transistor was realized, and that was not the field effect transistor. Okay, that was not on the principle of field effect transistor. It was something else. So John Bardeen, William Shockley, and Walter Bretton from the Bell Labs, they were working on the concept of this field effect transistor from Lilienfeld, but they were not able to create a working device. And there were some problems. I'll talk about that. So there were something called surface states, and they were not able to overcome that surface state problems. So, but in doing so, these two guys came up with a different device, which is called point contact transistor, which was named as point contact transistor. So it's not based on the theory of the field effect transistor. It's something else. It's very close to bipolar junction transistor, right? BJTs. Okay. So first transistor which was invented was close to the BJT, and you can see this picture of that, right? Shockley, and you can find this paper. So they published this in I think Physical Review, 1948. But you don't see the name of William Shockley here, right? So these two were actually, so he was the supervisor at Bell Labs, and these two guys were working under him. So he was more keen towards the field effect transistor. But these guys, they separately worked on and they created this transistor. Okay, so and published so many patents and papers and did not put his name. So he got a little pissed. Okay, he got angry. So what he did, he created his own version of the point contact transistor, which is known as the BJT now. Okay, so actual BJT came from him. Within an year, he created that. Eventually, all of these three are considered the inventors of the transistor. They got the Nobel for that. So 1956 Nobel was given to these three guys, right? And so there is this documentary, if you want to watch, very good documentary about the history of the transistors. Then in 1959, again a breakthrough came. Jack Kilby from Texas Instruments, an engineer, he created first integrated circuit. So you have a working device, a transistor, but people realize that if you want to make a circuit out of it, it should be compact. Okay, it should be on the same substrate, and so that on the same substrate you can put several things together: resistor, capacitor, transistors, diode on the same thing, so that your design become very compact. Not only that, it will also improve the performance, right? If the devices come close together, it's going to improve the overall performance of the circuit. So he gave the concept. Jack Kilby first IC patented in 1959, and after a few months, Robert Noyce from Fairchild Semiconductors, he also invented this integrated circuit. 1960 MOSFET demonstration. So first working MOSFET was demonstrated in 1960. So I told you that Shockley and other scientists, Bardeen and other people, they were trying to create this MOSFET but unsuccessful. So what was the problem? Problem was there were so many surface states. So say if I have these two terminals, right? This is say a piece of semiconductor. I have created two terminals here, and I want to apply some vertical electric field here, and if I directly deposit some metal here, right? So there is a huge lattice mismatch between the metal and the semiconductor. So you will understand what is the meaning of lattice and all of that, right? So people who already know, so probably you will appreciate more. So there is a huge lattice mismatch between this, and that creates a huge number of surface states here, defects. Surface states are basically unpassivated bonds at the surface. Okay. So if I talk about an atom, it is surrounded by all the other atoms, and its bonds are pacified. If I talk about say silicon atoms at the surface, from here its bonds are pacified, but from here it's a different material. So it will have some unsatisfied bonds. Okay, and that is going to create some unoccupied surface states, and eventually they will be occupied by the electrons. So it's going to capture the electrons. So that's going to create a charge sheet here, and when you apply some electric field, so that charge sheet will actually block the electric field, and it won't let the electric field go into the actual semiconductor. Because the electric field can't go into the semiconductor, you can't control the flow of electrons. Okay, so what they found, if we grow a silicon dioxide on top of the semiconductor, silicon, and then deposit the metal, it reduces the number of surface states. It actually creates a better lattice mismatch, a better lattice match, and number of surface states are reduced because of this cleaner surface, and now the electric field can penetrate into the substrate, and you can then control the flow of current. So a working MOSFET came in 1960, and Muhammad Atala and Devon Khan gave this first MOSFET demonstration, working MOSFET demonstration. Then again, a very important device, so floating gate MOSFET, which is used in flash memory or NAND flash, you can say, right? So Simon Z, the same guy, SNZ, the book I was talking about, and the same person, Devon Khan, they gave this concept of floating gate MOSFET, and which is very important for flash memory. So we use this device there. Later on, he became a professor in NYCU, retired, and he passed away only a few years ago. So he's considered a big pioneer because of his work in the semiconductor field. Okay, so this is about it. I won't talk about, there were several other innovations after that, but right, so we eventually moved from, so in the last 20 years, we had this planar bulk MOSFET, right? So it has one controlling gate, right, which is the third terminal, so-called third terminal in the Lilienfeld theory. And then you have the source and drain, two other terminals through which the current passes, and we can control the flow of current through. So current is going to go like this, and this is the controlling terminal, right, which flows, which controls the flow of current across this. And this used to be planar, one gate. Then we moved to FinFET. So around 2012, Intel came with the first commercial FinFET device, 22 nanometer FinFET technology. FinFET concept was known much before. So what is a FinFET? It has a fin type shape, right? So the flow of current is not through a planar channel like this. It is through this 3D body. So from a planar transistor, it became a 3D transistor, right? And you can have several fins, okay, because it has a fin type shape. And now the gate is wrapping this fin from three sides. So because now the gate, the metal gate, is wrapping this up from three sides, it has more hold on the flow of electrons through the semiconductor. So that creates a more electrostatic control, right? We'll talk about it towards the end of this course, but that gives it a more better control, increases the performance. So FinFET concept was again known back in 90s, but again it was real. It took how many, like 20 years for the industry to actually realize this. Okay, concept was known in 90s. My boss Chen-Ming Hu, so he played a major role in the development of this MOSFET, this FinFET. So he, along with his team in UC Berkeley, some other professors, so they realized first working FinFET actually giving a good performance, and you can find that paper in IEDM. So IEDM is a very big conference in our field, IEEE electron device meetings. You can find that paper. It has a huge number of citations. So you find a working MOSFET there, working FinFET there. So in 2001, FinFET was already published, working. But again, 10 to 12 years later, industry actually made it more robust, right? And industry does not move to devices so quickly because they have their own reservations, they have their own skepticism, whether this technology is going to be good or not, is it going to be good for their business? So a lot of things play a huge role. What is going to come next? Okay, is it going to be the upgrade of the same device, or is it going to be a new device? So industry has to do a lot of calculations before they move to the next technology node. So 2012, and then we saw several versions of the FinFET. So first was like 22 nanometer FinFET technology from Intel, then came the 14 nanometer. Before that, I think there was 16 nanometer also from Global Foundries. Then 10 nanometer, 7 nanometer, 5 nanometer, right? Intel used to be the leader. Now you know it's TSMC, right? So TSMC became a big player in the foundry business, semiconductor foundry business. And now we are talking about even more advanced MOSFET, which is nanosheet MOSFET, or it has several different names. Some Intel calls it nano ribbon, right? So it has a form of this ribbon. Some people call it nanosheet. Some people call it gate all around FET, because the gate is now wrapping this sheet from all the four sides. So it has even more control over the flow of electrons. Okay, more hold. So 2022, very recent, first shipment from Samsung. So Samsung is the only one today which is actually creating this nanosheet. Other companies like TSMC, so I think the nanosheet is going to come at their next node, but it's not yet there in the, you can say, you can't buy the FinFET technology, the nanosheet technology yet. Although they are doing the research, so it's almost about to complete. So if you look at, say, this A18, which is the processor chip in iPhone 16, so that's on 3 nanometer. Sorry, this is wrong. This is not GAA. This is FinFET actually. So 3 nanometer FinFET on TSMC process. So this N3E means 3 nanometer, but an enhanced version of that. And there is this processor from Samsung, Exynos 2500. So that's actually on the 3 nanometer gate all around process. So it is actually there. So that's about it. After this, we'll move to the actual stuff. So we'll talk about the crystal structure and all, a little bit of material science, and it will take probably 2 classes, and that's how we move.